are back with another EMAC tutorial, and today we're going to be looking at BaryCorrPy, precise barycentric correction for stellar and solar radial velocities and timestamps. So let's see what we got here. So what this tool does is it basically calculates barycentric radial velocities. First things first, we want to install the simple pip install. We already did that, and as you guys can see here on the side, they give us a lot of options that we can look at in case we have questions or how to get started and so on. A lot of things that it can do. It can do exposure meter calculations. It can also convert JDUTC to BJDTDB, and most importantly, it can calculate barycentric radial velocities. So we're going to click on getting started. As you can see here, the BaryCorrPy team left us with a sample script that I went ahead and put into Jupyter Lab, and this is how we're going to see and learn how to use BaryCorrPy. So again, we already pip installed it. So what BaryCorrPy can do, it is used to calculate the barycentric velocity correction for a star with an accuracy of less than 1 centimeter per second, which is pretty impressive. And how does it do that? Tons and tons and tons of math. So we're really glad that we have this at EMAC, because I don't know about y'all, but I do not want to do these calculations. So it takes into account the revolution of the Earth, the rotation of the Earth, the precession of the Earth, gravitational time dilation due to objects of the solar system. That's where it gets really tricky. Leap second offsets, proper motion, parallax, and the Shapiro delay effect, which is a special case of gravitational time dilation. And we will work off the script that they provided for us. And before we even start, we want to make sure that we have all the dependencies installed. So what you're going to need AstroPy, you're going to need NumPy, SciPy, JPLM-Fem, and AstroQuery. When you install BaryCorrPy, it automatically installs all of these, but it's always good to double check. So first things first, let's go ahead and see how we can obtain the barycentric corrected radial velocity for a certain star. First thing we'll want to do, we'll want to import all the modules we'll need. So from future import print function, import division, from astropy.time, import time, numpy as np, of course, and most importantly, from BaryCorrPy, import get bc underscore vel, so that would be barycentric velocity, exposure meter barycentric velocity, and UTC underscore TDB. And this last one is what is used to convert from UTC to TDB. And in case you don't know what that means, those are different time scales or units of times, if you will. So what they provided for us here in this script is a sample run of, or a couple of sample runs of how BaryCorrPy calculates radial velocities. And it's actually very, very simple. So what you're going to do, or what they did, was they gave us this line right here. So results is equal to get barycentric velocity of JDUTC equal to JDUTC. So that is our Julian date. And this is the number we went with. This is when this observation took place. The HIP ID is the Hipparcos catalog ID. And this one is 8102, and this refers to Tau Ceti. This is our star. This is latitude, longitude, and altitude for the observatory that took down that made this observation. And this observatory is the Cerro Tololo Inter-American Observatory down in Chile. You are going to set your ephemeris to DE430. That is the default. And this Z-mesh, this is the redshift measurement, and 0.0 is also the default. And down here, this loop is just saying if the result, this result 0 will be your barycentric radial velocity, If it is close to this, which is what it should be, then keep it. If not, we'll trash it. So that is one way that you can look for the barycentric radial velocity of this star, Tau Ceti. There's a couple different ways that you can do this too. Another thing you can do is you can define your time as an AstroPy list. So here, this is the Julian date format, JD, Julian dates, and the scale is in UTC. So that would be Universal Coordinate Time, something like that. It's in French, and unfortunately I don't speak French, not yet. So result 2 is equal to get BC underscore vel. Again, you are setting your Julian date. This is the same HIP ID, so it's the same star. And now we are going to name our observatory, which is the CTIO. Again, that is the Cerro Tololo Inter-American Observatory. So as you can see, there's a couple different ways that we can find these barycentric radial velocities. Sometimes you don't even have to put all these parameters in. Sometimes this is enough. So now another way that we can do this, if we want to, if we want to be super precise, or if we're afraid that maybe the first two aren't going to do it for us, we can go ahead and define all these parameters. So RA is our right ascension. We have our declination, the observatory name. We can leave that blank because with all the different parameters that we're about to put it in, it'll know what we're talking about. So the latitude of the observatory, the longitude of the observatory, and the altitude. The epoch, the proper motion in right ascension, and the proper motion in declination, the parallax of the target, the radial velocity of the target, and the measured redshift. So you can define all these parameters and then simply put them into just plug them in as arguments in your get underscore BC underscore vel, or get barycentric velocity. And as you guys will see down below, you'll see exactly what that yields. And the last thing we want to talk about here in this part of the script is the exposure meter calculation. So what this does is you define your exposure meter flux, and you use that to calculate the barycentric velocity correction for exposure. So this is our flux. Again, we go ahead and put all those parameters in here. This leap underscore update, that's just referring to the table of data. We want to make sure it's the most up-to-date one. Making it equal true will give you the most up-to-date files. And now we're going to scroll down, and we're going to see the first 4 results. And the rest of the results we'll talk a little bit more down below. So we're going to run this sample. We're going to run the sample. It's going to take a little bit because it is processing a lot. So this first right here, this corresponds to the first results. So if you guys remember, for the first result, all we did was give it our Julian date, our HIP ID, and the location of the observatory. And with all that, it knew exactly what star we were talking about. It gave us the barycentric radial velocity, along with the right ascension, declination, parallax, proper motion, and epoch, which is really awesome, especially this epoch, because sometimes this can be kind of annoying to look for, because you got to go to whatever database and try to find it. These warnings right here, so warning, assume input time is in UTC JD, pass AstroPy time object to avoid this warning. This is not a big deal. It's just saying, hey, you didn't specify what time we were looking at, but we're assuming it's this, and that's correct because that is what we were looking for in the first place. So right here, this is result 2. So we have the same star, so we expect the same stellar parameters. And this right here, again, is our barycentric radial velocity. Now, scrolling on down, result 3, So now we have 3 different barycentric radial velocities, all correspond to the same star, and this is what we would expect because in result 3, we gave it, where did you go? Here we go. We gave it 3 different Julian dates. So it was able to convert these 3 different Julian dates for us, given all of these parameters that we put in. Now, last one we want to look at for now is the result 4. So now, here we go. So now, again, we can avoid the warnings because we know what we're doing is correct. Again, same star, but now this first number right here, this is your barycentric radial velocity, and the second number right here, this is your barycentric velocity for exposure. So we are referring to, where did it go? Here we go. So it went ahead and calculated the barycentric velocity correction for exposure. And this can be very important to some of you that are actually observing stars. Not all of us get to have that kind of luck. So that's that. Now another thing we want to look at is you can also give it a star, Proxima b in this case, and use the get_stellar data, and it will give you all the data you need from Sinbad. And this saves tons and tons of time because you don't want to do that. How easy is it just to type this in and boom, it's right there, as opposed to having to Google it and search through a database to find all of these parameters. So moving on, BaryCorrPy also comes with a JDUTC to BJDTDB converter. And what does that mean? So Julian dates to barycentric Julian dates. And here's how it does that. So it uses a clock correction, so to correct for the difference between UTC and TDB timescales. Again, UTC is universal coordinate time, TDB is dynamical barycentric time. Yeah, it took me a while to memorize these. It also has a geometric correction, so light travel time from observatory to a solar system barycenter. Barycenter would be the center of gravity of our solar system, so the sun. And then the Einstein correction. So again, this is the hard part because relativity is tough. So this is a relativistic correction since Earth is not an inertial frame. We are going to import these modules. We already did this above, but this is just kind of here to show us like, hey, this is what you need to do. And all you do is you set your Julian date to your time of observation, what your Julian date. The format is in JD, Julian dates, and the scale is in UTC, universal time. You can think of this as like human time. This is like what's on our calendars. So we are going to use this module, this JDUTC to BJDTDB. This is telling it we want you to convert from Julian dates to barycentric Julian dates. And all you have to do is put in your time, your Julian dates. You are also going to define your star. It's the same star as before. And your observatory. Latitude, longitude, and altitude are all the same as before. So this is the Cerro Tolo Tolo Inter-American Observatory. Once again, man, what a cool name. So let's go ahead and see what that gives us. As you can see, it converted our Julian date to barycentric Julian date, and it also gave us all these stellar parameters as before. So that is BaryCorrPy. You can find it on the EMAC homepage. Whoops. You can find it on the EMAC homepage. If you guys have any questions or suggestions for the next tutorial, you can also go to our vote page to vote for what you want to see next. Make sure you follow us on Twitter at ExoPlanetModels and subscribe to our YouTube. Thank you and have a great day.